Hi, everybody. My name is Jacob Jones. I'm a PhD student in AMS and IACS. I work with Dr. Zhao and with Dr. Rebecca Conley at St. Peter's University. So my research is in the superconvergence of hybrid spectral elements. So it's been known for quite some time that spectral elements superconverge for tensor product elements. So these are cubes, squares, high order than that. And the issue is that if you distort these tensor product elements pretty much at all, they lose that superconvergence. So it makes mesh generation extremely tricky when you have irregular domains or domains with curved boundaries for spectral element method or finite element method. So to contrast that, in 2016, Dr. Conley and Dr. Zhao came up with the ACEPM method, which is far less sensitive to irregular boundaries. So the main difference between ACEPM and SEM and FEM is the basis functions. So ACEPM uses generalized Lagrange polynomial basis functions, where SEM uses regular Lagrange basis functions. So our idea was to combine SEM and ACEPM to form a hybrid method, which we called SPEEF, which stands for Spectral Element Enhanced ACEPM. And SPEEF kind of simplifies mesh generation, because what we want is these regular tensor product elements in the interior while having simplicial elements near the boundary. And the way SPEEF works currently is we find an initial solution using SPEEF using SEM on the entire domain. And then we take a subdomain near the boundary, and we use the initial solution from SEM as boundary condition to do ACEPM just near the boundary of the subdomain. And then what we can do after that is we can iterate between SEM and ACEPM by switching back and forth between these domains of interior tensor product elements and the simplicial elements near the boundary. And what we find when we do this is that SPEEF preserves the global superconvergence of SEM in the interior while recovering the same order of convergence near boundaries at minimal extra cost. The reason it's minimal extra cost is because to form the stiffness matrix in 2D, it requires ON squared quadratic complexity. But because ACEPM is only working near the boundary, really just in a distance from the boundary, it's linear complexity comparison. And that's pretty much it. Does anyone have any questions? Thank you.
Actually, I had a question back at the beginning about the generalized Lagrange function. I mean, so I think about the FEM is sort of almost dividing up the volume. But once you have a curved surface, how does it go about actually preserving that partition?
They're kind of similar to weightedly squares. So it's more of a generalized finite difference method. And those basis functions, they actually extend further. So the stencil for each point is a lot bigger than standard FEM, but it's far, far less sensitive to curved boundaries. But of FEM, not SEM.
And if I understand correctly, this ability to maintain the order of convergence globally,
yes,
it is huge. I mean, there's not that many, if any, other methods that can do this.
Yeah, that's why we're really excited about it, because it's the first time that's been done. And especially, I think another important aspect is that simplification of mesh generation. Is a lot of time and money goes into generating these really pretty looking meshes, but when you can simply just fill the interior with squares, and then near the boundary, it doesn't have to be a perfect mesh, it just has to be a good enough mesh that ACEPM can kind of take it.
So on these regular meshes, can you just use like global spectral methods like Fourier transform? Not completely uniform grid that's now numerically optimal.
I don't know. I'm not sure. Yeah, because